Hello, I'm Nikki Crange, a fellow of the SEAS program at NC State. In this video, we will briefly go over some of the basics of atomic structure and crystallography. To start off, let's define a few terms. A material that lacks any long-range order is called a non-crystalline or amorphous material. We can see that there is some short-range order where the center yellow atom is surrounded by 3 blue atoms, but when we look further away from the center atom, there isn't any repetitive periodic structure. One example of an amorphous material is glass. On the other hand, a material that has translational periodicity and long-range order is a crystalline material. One example of a crystalline material is diamond. In crystalline materials, a unit cell is defined by the smallest unit of volume that, when repeated in all directions, fills all space. For example, if we were tiling our kitchen, this hexagon would be our unit cell, and we could fill our entire kitchen by translating this unit cell in all directions. Similarly, the same thing can be done with crystalline materials. In this case, the highlighted square is the unit cell. The unit cell can be represented by a lattice. A lattice is just a mathematical representation of the unit cell, where the location of any lattice point in the volume can be found by a linear combination of integers and unit vectors. In this case, x, y, and z are our unit vectors, and alpha, beta, gamma are the angles between the unit vectors. There are 7 different lattice types, each characterized by the magnitude of their unit vectors and the angles between them. We can see that there are varying degrees of symmetry between all the lattice types, with cubic being the most symmetric and triclinic being the least symmetric. A basis is the atom or group of atoms that occupy the lattice points. There are 4 basis types: primitive, body-centered, face-centered, and side-centered. A primitive basis has 1 atom on each lattice site. Body-centered has an atom in the center of the volume. Face-centered has an atom on the center of each face, and side-centered has an atom on the center of 2 faces. Each lattice type has an inherent symmetry. The basic types of symmetry operators are 2, 3, 4, and 6-fold symmetry. We can see that after n operations of an n-fold symmetry, we get back to the original shape and can't tell that anything has happened to it. There is also additional symmetries, such as reflection and inversion, that help fully describe the symmetries present in a given crystal structure. When we combine the 7 lattice types and 4 basis types, we end up with the 28 possible combinations. Of those 28 combinations, only 14 obey the inherent symmetry of the lattice type. These 14 combinations are called Bravais lattices. Every crystalline system will have one of these lattice types. Now that we have defined our lattice systems, let's understand how we use them. In a unit cell, the length of the unit vectors are normalized, and fractional coordinates are used to define a direction. Square brackets are used when writing directions. Let's go through one example. First, find the endpoint of the direction from the origin. Next, find the intercepts of the point with each axis. Here we see that the point is 1/2, 1, 1/2. We then multiply by the common denominator, giving us 1, 2, 1. If the value is negative, we add a bar over it and finally simplify it to the lowest divisible number. In this case, we will end up with 1, 2, 1. A plane is defined by 3 points in the unit cell. Parentheses are used to identify a plane. Let's look at an example. Again, we start with finding where the plane intercepts the axes. Next, we take the reciprocal of each intercept. If the value is negative, we add a bar over it and finally simplify to the lowest divisible number. Now that we have a handle on this, let's look at a slightly harder example. We start just like last time by finding the intercepts of the plane. Here we see that the plane intercepts the x-axis at 1/2 and the y-axis at 1/2. In this case, we never cross the z-axis, so we say that the plane crosses the z-axis at infinity. We then invert the intercepts, So we have 2, 2, and 1 over infinity. This gives us a plane of 2, 2, 0. We can now simplify and get the final notation for this plane as 1, 1, 0. Working with planes in real space can be difficult. Therefore, we use a mathematical construct called reciprocal space to more easily understand and interpret crystal structure information. The most common place reciprocal space is used is when working with diffraction data and finding the spacing between planes. We can get to the reciprocal space by performing a Fourier transform of real space. An example of this kind of transform is going from the time domain to the frequency domain. The derivation of this transform can be found in a variety of resources, so we won't go into detail here. We will do one quick example before wrapping up. Let's consider a 2D lattice with unit vectors a and b. We can see that after the Fourier transform, the long direction in real space, a, becomes the shorter distance in reciprocal space, and the opposite happened for b. Once we have done the Fourier transform, we can then do a variety of calculations involving the crystal lattice directions and planes. That's going to wrap up for this quick introduction of atomic structure and crystallography. Thank you for watching.